Started. Hi everyone, welcome to the second to last lecture of cs224n. This one's on a topic I'm particularly interested in and excited about, which is semi-supervised learning. We have a few announcements to start. So obviously the final project is due super soon, it's due Sunday, so please come to office hours. Richard is holding office hours after class in the usual place for as long as it takes. You can also come to mine or Abby's or Tim's office hours with project questions. And if you're doing the default final project, you can go to any office hours with questions. I guess from the looks of it, a lot of people are at home working on their poster session now, or on their project now. Also, the final project poster session is coming up soon. It's coming up in a week. There's a bunch more details about that on the website now. So things like the logistics of it, what you should put in your poster, what you should do if you can't make the poster session. The one piece of urgent action is that if you can't make some of the poster session or can't make all of the poster session, there's a Google form we're asking you to fill out as soon as possible so we don't accidentally give you a spot in the poster session only to have you not show up. And if you're not going to the poster session, the alternate way of submitting your work is through a YouTube video. And we'll be playing those during the session so people will still be able to see what you did. Okay, on to today's lecture. So I'm going to start off with some motivation of why is semi-supervised learning good and why you should use it for NLP. And then we're going to cover 3 kinds of semi-supervised learning algorithms. The first one is called pre-training, which has had a lot of recent success with really good results. Then we're going to cover self-training, which is not so commonly used these days, but has a lot of historical importance, and a lot of other semi-supervised learning algorithms use the ideas from self-training. And then lastly, we're going to cover consistency regularization, which is a recent semi-supervised learning algorithm that's also been pretty successful. So I want to start off with a broader question, which is why has deep learning been so successful recently? So I really like this comic. Essentially, there's a statistical learning person in the top, and he's working really hard coming up with a really complicated, principled, theoretically motivated approach. And then there's a deep learning person at the bottom, and he just says, stack more layers, and that's all you need to do. And that's a little bit been the story of deep learning, is that deep learning seems to scale really well with both data size and model size. So this is sort of a cartoon graph that illustrates it, where in the x-axis it's scale, y-axis is an accuracy. And certainly all machine learning methods benefit from scaling up, but it seems like neural net methods are particularly benefit from it. So you can say in the 80s and the 90s, when people were working on neural nets, but they weren't nearly as successful as they are today, we were where that dotted line is on the graph. And then these days we've moved past it, and now neural net methods are really becoming commonplace. So I don't think it's entirely been a matter of scale. There are also tricks and research ideas that have certainly led to this. So especially things like dropout and improved optimization, ideas like attention. But a lot of it has been due to scaling up. So hardware has gotten better, which means we can train bigger models. That's actually partly thanks to video games, is that we've developed really good GPUs, and then we can use those GPUs to train deep learning models. And these days, there's a lot of interest now in building hardware that is specifically designed for deep learning systems, like Google Cloud TPUs, which can do even fewer operations effectively, but the ones they can do, they do really fast. So things like matrix multiplies and convolutions, because those are what we need in our neural nets. The last point, and this is the point I especially want to talk about today, is larger data sets. So let's take a look at 3 of the biggest deep learning successes, arguably at least. So one is image recognition, right? In the old days, you would have to do a lot of feature engineering, write edge detectors, that kind of thing. These days, an end-to-end neural network gets essentially human performance, at least on standard image recognition tasks. For machine translation, neural networks have about halved the gap in accuracy between human translation quality and the translation quality from older phrase-based neural machine translation systems. And then lastly, game playing has got a lot of press. So DeepMind built some AIs that could play Atari games. And there's also a famous AlphaGo AI that achieved superhuman performance at the board game Go, which many people were pretty surprised and impressed by when it first came out. What I want to point out, though, is that all of these successes have been driven by really large amounts of data. So for image recognition, the main data set that led to that success was ImageNet, which was actually developed here at Stanford. And that has 14 million images with labels. So really massive data set, and that is what allowed us to train such good models. For machine translation, there are the WMT data sets, which are also in the size of millions. And you can imagine for other systems, say Google's machine translation system, they have their own sources of data which are even larger. And then for these game playing AIs, it turns out they're actually extremely data inefficient. So in order to get these kinds of amazing results, the AIs have to play the games millions of times. So not at all how a human learns a game. And even though they end with impressive results, it doesn't come very easy. So what I want to do is compare these successes with these enormous data sets to what most of NLP data sets look like. And essentially, they're much smaller. So here, the data sets are for pretty core, pretty well-studied NLP tasks, like named entity recognition, coreference resolution, parsing, and so on. And these are for English, which is the language where currently there's the most resources in terms of annotated data. But even despite that, you can see the size of this data sets are 1 to 2 orders of magnitude smaller than those previous ones. So around 10K to 100K examples. And of course, there are many other tasks we would like to train NLP systems for, and those typically have much smaller data sets. And on top of that, there are many other languages beyond English we would like to train our NLP systems on. Currently in NLP, certainly the main language that's studied is English, and there's lots of other work on multilingual NLP, but I think there's still a really disproportionate focus on English, given that less than 10% of the world's population actually speaks English as their first language. And these issues I was mentioning before of small data sets is much worse for languages that are less frequently spoken. So this is actually, I think, one of the real bottlenecks that's preventing deep learning from taking over NLP completely, is because in most cases data sets are small, and deep learning methods don't work very effectively on smaller data sets. Okay, the question is, what can we do to solve this? And well, one answer is to say, we just need to collect more data. But of course, in practice, this is a really expensive thing to do. You need to somehow pay people to label the data. And across a lot of languages and a lot of tasks, maybe you can collect small amounts of data, but getting to that stage of millions of examples that have led to other deep learning successes really isn't that reasonable. To make matters worse, for some of the tasks, say parsing, you can't have anybody label it. You can't do crowdsourcing. You need a linguist, or at least someone who knows enough about linguistic theory that they can provide those annotations. So what this lecture about is an alternative idea which allows you to train a model on more data, but a lot of that data won't be labeled. So essentially, you can go to the web or go to news articles or anywhere else, collect a bunch of sentences in whatever language your system is on, and have your system try to learn in a more unsupervised way from those examples. So this makes a lot of sense for NLP because there's tons of text data out there. So finding the unlabeled data is easy. And semi-supervised learning uses those unlabeled examples. So I'm going to start with a little cartoon example of what semi-supervised learning looks like. And this will be a running example throughout the talk when I'm discussing some of the algorithms. In this data set, there's a red half circle and a blue half circle, and they kind of overlap. So the goal is for the classifier to predict, is a given data point going to be red or blue? And it being a semi-supervised learning scenario, we would only have a couple labels. So here we have a few points that are red or blue, which means they're labeled. The rest of the points are black, which means they're unlabeled examples. So from the perspective of a supervised classifier, if you just try to train it on this data set, it would only see these 6 points. And really, this is not much for a classifier to go off of. If you trained a model on it, it would probably end up with this sort of decision boundary, which is just a line separating the 2 sets of 3 points. And of course, this isn't actually the correct decision boundary. When you actually look at the data, the model makes quite a few mistakes. So the rest of this talk is how can we do better than that? How can we look at those black points in training and learn a more effective model? OK, so I mentioned these methods at the beginning of the lecture. But we're going to be covering 3 approaches to semi-supervised learning. So the first is pre-training. This was actually used a lot in the old days of deep learning before it became really successful, or in the early stages of it becoming successful. And actually, you learned about a pre-training algorithm in week 1 of this class, which is word-to-vec. So word-to-vec, you using unsupervised learning, learn representations for words. And then in a second phase, you incorporate those words into another supervised model and perhaps continue updating those word embeddings during training. Self-training is a very old idea for semi-supervised learning, going back to the 60s. It's not so commonly used today, but I think it covers some important concepts about semi-supervised learning. And then the last algorithm we're covering is consistency regularization, which is a recent idea that's seeing lots of active research, and it works well for vision and NLP. Before I start going into the algorithms, any questions so far? All right, I will keep going then. OK, so the first semi-supervised learning algorithm we're going to talk about is pre-training. And the idea is to train the model in 2 steps. So first, we're going to train a model that only looks at the unlabeled data and uses unsupervised learning to learn some weights. And then secondly, we're going to train a supervised model that only looks at the labeled data. And the thing tying those 2 steps of training together is that some of the weights learned in the first model will be incorporated into the second model. And optionally, you can continue fine-tuning that second model in training, or you can keep its weights fixed, sort of like you can do with glove vectors. So I mentioned earlier, word-to-vec, which you learned about earlier, is exactly an example of this method. So in this case, the part of the model that's shared between the first phase, the pre-training phase, and the supervised learning trades are the word vectors. And the algorithm used to learn those would be skipgram or continuous bag of words or glove or whatever other embedding algorithm you're using. And then the supervised part of the model is, say, your LSTM or whatever else you're using for the task. And when you train that supervised model, usually you would initialize the weights for the embeddings using glove vectors. I want to provide some intuition for why actually is this a good idea. One way of thinking about it is that the comparison point to pre-training, so the comparison point to initializing your model with glove vectors, is just initializing your model randomly. So clearly it seems like pre-training has to be better than random initialization. Another way of thinking about it is that pre-training gives more meaningful inputs to the supervised part of your model. So for example, glove vectors already contain a lot of information about word meaning, and the supervised model can exploit that during training. So a really common setup is what's shown here in the figure, is the pre-trained model. The supervised part of the model is stacked on top of the pre-trained part of the model. So you can say that the inputs to the supervised model, instead of being some raw data, are vectors from a model that's hopefully learned better representations. So going back to this 2 moons data set, what we could hope is that if we did some pre-training with a good objective, the model would learn a more effective representation space for the data points. So essentially what that means is if you just look at the raw x and y coordinates of the images or of the points and you try to make a decision boundary, you're going to do it wrong. But if you feed in some really nice representations that capture more meaning about the data, the classification problem for the supervised part of the model gets a lot easier. Okay, so let's go into applying this sort of algorithm for NLP. Here's a very rough schematic of what most NLP models typically look like. What you've already seen before and should be familiar with is just pre-training the word embeddings. So that part of our model is going to be learned during some unsupervised training phase. The rest of it is trained in supervised learning. And essentially what recent work has started looking at is can we actually pre-train more of the model, such as some of the LSTMs inside the neural network. And if we do this, shouldn't that work better than only pre-training the word vectors? Okay, so I'm going to start going through a few recent papers that have tried out different variants of this idea. So this one from 2015, the pre-training step is done with an autoencoder. So an autoencoder is essentially a seek-to-seek model, but the output sequence is actually just the same as the input sequence. So if the input is "it was good," as in this picture, we're training our model to encode that sentence into a vector and then decode that vector back into the original input. So really crucially here, this seek-to-seek model won't have attention, because if it did have attention, it could learn just to copy over all the original words, right? And it wouldn't probably learn anything useful in its LSTM. So that's the idea of this pre-training phase, is the LSTM encoder here has to convert the input into a really meaningful vector, because it has to contain all the information the decoder needs to be able to get back out the original input. And then that's the pre-training step. For the supervised learning step, this paper just took that encoder in the seek-to-seek model and added a softmax layer on top to produce some classification about the sentence. And they evaluate on several sentence classification tasks. Any questions about this model? All right, still good. Let's keep going. So here are the results from this model on a couple different data sets. So the left most common is the best results from previous work. And you can see if you just train a standard LSTM supervised model, you get the results in the middle column, which are noticeably worse than prior work, because it's a pretty standard, simple baseline. But if you first pre-train the encoder and then continue training the model for the supervised task, results actually improve a lot. So enough that it's state-of-the-art on all of these different tasks. Okay, so that was one variant. Here's another kind of similar approach. So this was actually done by Richard and others. The method is called cove. So it still could be viewed as this weight initialization scheme, but there are a few really important differences. One is that in this pre-training step, the goal is not auto-encoding, it's machine translation. So actually, I think you probably couldn't call this a semi-supervised learning method because in machine translation, you have labels. You have both the source and the translation. So really, this would be considered transfer learning, but I'm still presenting it here because it is extremely related to these other approaches. Two other details. Number one, they actually don't continue training the LSTM encoder on the supervised data. And next slide, I'll talk a little bit about why that's actually a really useful idea. The second thing they do is for the supervised part of the model that's on top of the pre-trained encoder, they train not just a softmax layer, they train kind of a whole nother model essentially. So it'll have its own bi-LSTM layers and softmax layer making the prediction. So here is a little bit more on why should we not fine-tune this encoder during training, because it seems like surely updating it is a good idea. Usually with glove vectors, updating them is a good idea. And one answer is actually just efficiency, because if you keep that pre-trained encoder fixed, then you only need to run it once over each example, and since it's not training, its outputs are never going to change. So this makes training really fast. Essentially what you can do is run the encoder, and from that point on, just treat the outputs of that encoder like glove vectors, right? They're just inputs that go into the model, and you can kind of forget that there was some big bi-LSTM that was trained for machine translation actually doing that conversion of words into vectors. So this is where the name cove comes from. It's contextualized vectors. So it's like glove in that we are producing meaningful representations for words that are getting fed into the system. But it's contextualized, meaning that because there is a bi-LSTM that's running over the input sequence, the representations for the words contain some context information. Because that's what bi-LSTMs do, is they map whole sentences into representations, not just individual words. Question?
How have people tried this, where the final step is not sentiment, but what's it called, where you're figuring out if it's a noun or a verb?
Part of speech tagging?
Yeah, part of speech tagging and that whole sort of syntactic structure stuff. It feels like that should also be really relevant and work.
Yeah. So the question is, what other tasks besides sentiment analysis could you do this to? The answer is a lot of tasks. So actually this paper in particular, well, we can just go to the next slide, has already done it on a lot of tasks beyond sentiment. So SST is sentiment, and so is IMDb. But SNLI is textual entailment. Squad, you are all extremely familiar with. It's question answering. And this approach is useful in lots of different tasks. Actually, later on, we will show part of speech tagging results as well, I think. Maybe. But anyway, the results are actually really impressive. And just to provide a little bit more information about this graph, the height of each bar shows how much do the using the pre-trained representations improve over random initialization of the vectors. And you can see that glove works really well. But if you also throw in these other representations produced by a machine translation system, you get nice gains across all these different tasks. So it's a really general purpose method that could be used for a lot of different models. Another question.
My question is that, is this like just stacking another layer of LSTM, just not taking that image?
So the question is this just stacking another LSTM layer in the model? I mean, the answer is essentially yes. We're now adding, well, I guess maybe this picture shows it better. We're adding a new layer to the bottom of the model. And that one is pre-trained rather than updated during training. The rest of the layers will be just standard, random initialization and then learned with supervised learning. And another question?
When that pre-training layer is worse for performance than the simple network without it.
Are there cases where pre-training hurts performance? So that's a good question. I'm not actually aware of anybody who's done those experiments and found counterexamples. I know at least with pre-training word embeddings, in some cases it doesn't help. So for something like machine translation, or in general where you have a really large amount of data, the pre-training isn't necessary because really the main advantage of pre-training is exposing your model to more data so it learns more about language. So I don't know of cases specifically where performance gets worse, but there are at least going to be cases where it probably doesn't make any difference to the performance. So what?
I mean, it's not an often thing to happen when we have worse performance. Okay.
Yeah, I mean, not that I've seen in these experiments and also other experiments. So yeah, it seems like in general, this is a really good idea, and this should be more commonly used in NLP. Yeah, I mean, it's a very recent idea, which is probably why it hasn't caught on, right? So this paper is from 2017. So my year is wrong in this first slide, but this paper is actually from 2018, a couple months ago. But this is also a pretty similar approach, but again, there are a few differences. Number one, the task that is being pre-trained is language modeling rather than machine translation or autoencoding. One thing they do is actually do language modeling in both directions. So in class, I think you've only seen predicting next words given the previous words. There's no reason at all you can't do that backwards and start from the end of the sentence and try to generate it right to left rather than left to right. A few other details that are different about this approach. One is just the scale of it is much larger. And I'll give some numbers on it later, but really the language model they use is enormous and trained on many GPUs for many days. And then there are a few other tricks I'm going to get into. ELMO, by the way, stands for embeddings from a language model because they use language modeling as the pre-training step. Okay, so here is an overview of the tricks I mentioned. So trick number one, instead of only training the language model on the unlabeled data, they also fine-tune it by running it for, let's say, one epoch of one pass over the data set on the supervised data set. And that somehow tunes the model so it's more relevant to the particular task you're going to do supervised learning on. The second thing they do is they combine the representations from the language model in a bit more of a complicated way than previously. So remember, previously, right, it was the pre-trained embeddings are just going straight into the model like word vectors. What they do instead is, number one, there's a weight that just says how important are these pre-trained embeddings versus the other embeddings, which should be glove embeddings typically that are going into the model. So that's what the gamma parameter is. And then the second thing is their language model is a multi-layer neural network. And they add some weights basically controlling which of these layers are contributing most to the final representations that are going into the model. As opposed to in the previous example, that would just take the top LSTM's layer output. But actually, it seems to work a lot better if you allow the model to look at all the layers in the pre-trained model. The last trick they do, which also seems to help quite a bit, is instead of passing in the ELMO representations once, so just passing them into the first layer of the supervised part of the model, they pass it in at multiple places. So maybe to the final softmax layer in addition to the first layer. So I guess you could say there's nothing hugely different about this approach than the previous approach. It's just kind of a bunch of little tricks that all work together really well. But when you combine them, you get like extremely impressive results by NLP standards. So they train models on 6 tasks, And one thing impressive about this is there's a real diversity of tasks, everything from coreference resolution to named entity recognition to squad. And across all tasks, if you look at the rightmost column, you can see that the improvements are actually really large in terms of relative performance. For most NLP papers, each one of those individually would be a great result and a good paper, and this is across a whole bunch of different tasks. They end up with state-of-the-art results in all these tasks. So this, even though it's a few months old, only a few months old, has actually gathered quite a lot of excitement in the NLP community, and there's sort of speculation that this kind of method is really going to become a standard practice trick the way glove vectors are a standard practice these days for doing these NLP tasks. Any questions about this? Sure.
Like, this seems very similar to what babies must do when learning language. So certainly a lot of unsupervised learning, and probably this kind of unsupervised learning in particular. Has anyone done like back of the envelope kind of how many words does a baby on average hear when they're growing up? There's unsupervised and then supervised, and how does that compare to what this is achieving, and how close are we to the baby benchmark?
So yeah, that's a really interesting question. Yeah, so the question was, well, first of all, this kind of approach is maybe similar to how humans learn, where most of human learning is unsupervised, and maybe a little bit you actually get feedback from the world or from a teacher or something. And is there any numbers on how much do babies learn unsupervised versus supervised? And is there a comparison point to these models? I don't really know the answer to that. I mean, I think it's probably really hard to quantify how much data does a baby receive as input. So I'm not sure about the answer. I think you could look up, how many words they see before they start actually learning language. But yeah, I think that's actually a good point to make in general. And a lot of people in the ML, the machine learning community, are talking about this, is how it seems like humans really rely on a lot of unsupervised learning, and shouldn't our deep learning systems also do this? Okay, so here is just a brief summary of pre-training, because we're going to move on to other algorithms. The idea is really simple, right? You just train one model and incorporate it into a different model, and that's it. And the results are really impressive. I do want to point out that there's actually a pretty significant downside for this kind of approach, which is that you need to train a separate model, and that model is typically really large. So for example, with Elmo, it uses a 2-layer BioSTM with 4,096 units in each layer. So the hidden layer size is 4,096. They also have a character level convolutional neural network thrown in there, which is also really large. And in order to train it, it requires 10 epochs of training over a 1 billion word size corpus. So one downside is the annoyance of training this big thing. At least once you've trained it once, you can use it for a bunch of different tasks. So that alleviates this a bit. Also at test time, right, you have to run some really giant model. So maybe there are questions of, if you're actually trying to deploy a deep learning system in practice, how feasible is this idea? But still, yeah, the results are really impressive, and I think there's a lot of potential for this sort of method. Okay, so that was pre-training. We're going to move on to the second semi-supervised algorithm, and that's called self-training. Here, we're not going to have 2 phases of training, so that simplifies the method, makes it a little bit more scalable. I've said this before, it's a really old algorithm. It's basically the first and simplest semi-supervised learning algorithm, and the algorithm can be stated really simply in 3 steps. So first, you do regular supervised learning on your data set. Then you look at the unlabeled data, and you have the model basically train itself, which is where self-training comes from. It will train itself by labeling those unlabeled examples, and then we'll take a few of those and add them to the training set. So the model's labels on these examples are going to be noisy, because the model isn't as smart as the person, but the hope here is that those self-labeled examples are still better than nothing, and the model can sort of bootstrap and improve performance by doing this process. So going back to our toy data set, first step is we train a supervised model, and we get something that's mostly wrong, but is at least a little bit right. Then we can use it to label a few of the examples in our data set, which is going to look like this. And now we can train our model again, and because it has these additional labels, it's going to do a little bit of a better job of learning what the decision boundary looks like. So now it's pretty close to being correct, and we can repeat this process, right? So now we can label a few more examples. We can learn an even better decision boundary, and at this point, our model is now getting the whole data set correct. Okay, so I guess I mentioned this isn't commonly used these days. Back in the 90s and 2000s, there was actually quite a bit of success of applying this sort of method to NLP tasks. So just for one example, the table on the right there shows the F1 score for constituency parsing when you give it increasingly more training data in terms of unlabeled examples. So from 50,000 going up to 2 million, you don't see necessarily enormous gains in accuracy, but you do see some. I guess the question is, why isn't this very commonly used these days? And the answer, I think, is really that there are other methods that work better, not necessarily that there's any real problem with self-training. So to move towards talking about a better version of self-training and a one that fits in better with neural models, one thing to think about is this process of training your model multiple times, right? You train the model, label some examples, then you have to train the whole thing again. With a neural net, that gets really slow, right? Because neural nets take forever to train. So here is a online version that doesn't have that problem. And the way it works is we're going to take a mini batch of labeled examples, so input xi with labels yi, and an unlabeled mini batch, which we're calling xj. And then we're going to minimize the following loss function here. So the term that's most to the left in the loss function is just regular supervised learning, where you're training the model to produce this one hot label that's a human-provided output. On the unlabeled example, we're going to perform inference with our model, so have it produce some prediction about the example, and then turn that into a one hot label. And this is a noisy label, but again, we can still hope our model learns from it. And then otherwise, again, we're just minimizing cross-entropy loss. Any questions about this particular way of doing self-training?
Do you have any intuition on why this works? Like, I can sort of, it seemed weird. There's something sort of suboptimal about the way of doing it normally that means I can somehow learn from itself.
Yeah. So that's a good question. I guess the example earlier with the picture is some kind of intuition. It's basically that the model can somehow bootstrap from its own predictions. So I guess one way of thinking about it is you're dramatically increasing the size of the training set because there's much more data the model is learning on. And there's a trade-off in that that increased training set now has less accurate labels because they're produced by the model. But I guess the benefit of a much larger data set outweighs the disadvantage of having noisy labels. And that's kind of an intuition of why this works. Another question?
Online self-training works, and how is the first cost that can be minimized at the same time as the other?
So the question is, how does this actually work? How do you minimize two losses at once? I mean, the answer, I guess, is in the equation that you sum them up. And for each step of training, your model now has two inputs instead of one input. So typically, you would only have the labeled mini batch xi as input. In this case, you run the model twice and sum up the losses and still perform gradient descent as normal.
So it's still running.
Yeah, it's still running twice. You could alternatively actually just do one step then the other. So first take a mini batch of labeled examples and optimize the left-hand side, then take a mini batch of unlabeled examples, do the right-hand side and alternate between the two. I think that would also work fine instead of summing them up.
What's the most common technique for choosing these XJ labels? I mean, do we actually use just the rest of the data set on each time or every time we produce the labels, or just like small subset? And if it's small subset, how do we choose that?
So the question is, where does the XJ come from? So it could be the same data set as the XIs, and you could take small portions of that. That isn't as useful as actually finding a separate, much larger data set to do semi-supervised learning on, because this way you're exposing your model to more data. So usually you would try to find a source of data that's similar to your supervised data set, but without labels. So if your supervised data set's on web text, you'd probably want your unlabeled data to be web text, and you'd scrape the internet, get a bunch of examples, and feed in one mini batch at a time. And you can, I guess, the size of the mini batch would be a hyperparameter you would have to tune. Okay, so I mentioned this isn't very commonly used, but it actually is really similar to other algorithms. So really, the rest of this lecture, the overall loss function is going to look the same, except we want to make that right-hand self-labeling side better. So the first thing we could try is wonder, why are we dealing with this one-hot argmax nonsense in the right-hand part of the equation? Wouldn't it make more sense to actually train the model to produce a probability distribution? And basically the reasoning is that a probability distribution actually contains a lot more information than a one-hot label. Because the one-hot label only tells us which class is most common. A probability distribution tells us other things like which class is the second most common and how confident is the model in its predictions, that kind of thing. So we could do that in this equation, right? We just delete the one-hot argmax and end up with this loss. But actually, this loss looks really silly because in this situation, the two parts of the cross entropy are actually the same. It actually turns out this works as a semi-supervised learning algorithm, but I think intuitively it looks really odd, right? We're training the model on labels, but it already matches those labels. So what's actually going on there? So what we are going to do instead, and this is the third algorithm I'm going to present today, is it's called consistency regularization. And the loss is going to be like that kind of silly example from before, where the target the model is trying to learn is a probability distribution. So we would call it a soft target rather than a hard target, which is a one-hot label. But now we're going to change something in the other part of the equation, which is we're going to add noise to the input of the model when it's acting as kind of the student, when it's trying to learn to produce the left-hand part of cross entropy, which is the target. So yeah, just to provide a little bit more information, what does that noise usually look like? Here it's written as eta. Typically, you could do something like this. You could say it's a vector with random direction and then some small magnitude epsilon. So let's think a little bit of why is this a good idea? Why would this work? And essentially, what this algorithm is accomplishing is training the model to be robust to noise. So we're saying that if we add this little bit of noise to the input, it shouldn't totally screw up the model's predictions and have it predict something totally different than it did without the noise. In other words, we're saying that for every random piece of noise, so in other words, in some ball around each data point, the model should be giving essentially the same label. And if you think of this in terms of computer vision, I think maybe it's a little more intuitive. You're basically saying, if you're asking a model to classify an image, and then you tweak all the pixels a bit so they look slightly different by adding a tiny bit of noise, the model shouldn't suddenly go from thinking it's a picture of a cat to it's a picture of a dog. So I think the motivation behind it is pretty intuitive. A term you see for this kind of technique is distributional smoothing, because by saying the model has to give consistent predictions to nearby points, is saying that the output distribution with respect to the input has to be smooth. You can't shift a little bit of the input and suddenly completely change the output. Yeah, question?
If you replace the target here with this normal label supervised setup, this would still be a really good idea, wouldn't it?
Yeah, that's a good point. So the point is here, on the left-hand side of this equation, you could actually just do this for supervised learning as well and say the model should be robust for noise then. Yeah, that has actually been studied and tried, especially in the context of adversarial examples, which I'll actually talk about later in this lecture. Okay, so why does this work? Go back to our example yet again. So here's our data set. And remember what this additional loss term is saying is that if you're in one of these balls, the model should not be changing its prediction much. So in particular, you could say sort of by induction, for all of these balls that are overlapping, the prediction has to end up being the same. And of course, some of these already have supervised labels in them. So from this, we can basically conclude our model's decision boundary has to look like what's shown in this image, where we get the correct classification. All the points that should be blue are blue, and all the points that should be red are red. So I mentioned, I guess, computer vision is kind of an intuition for it. This approach works really, really well for computer vision. So here are results on a fairly small computer vision data set called CFAR10, which has 50,000 examples. And basically, what people have done here is just thrown out most of the labels. So there are only 4,000 labeled examples in the training set, and the rest are unlabeled. And then trained a model with various approaches and seeing how they're done, or seeing how well the model works. So a supervised model doesn't do well, which is not surprising because it only has 4,000 labels and it's a deep learning classifier. And then you can see there's been a bunch of previous work here using kind of generative approaches. So I'm not going to go into detail what they are, but they use things like GANs to improve the model's learning. And then the last number there is this consistency regularization idea I just talked about. And it's something like a 1/2 to 2/3 error reduction compared to prior work. So awesome. This is super good for vision. The next question is, can we take this idea and apply it to natural language instead? And actually, this is a little bit tricky, right? So at the top, we still have our loss function. That's what we do to optimize for consistency regularization. But note that for NLP, the input xj is a sequence of words. And what does it actually mean to add noise to a sequence of words? That's actually really hard to define because words, unlike pixels in an image, aren't discrete. So you can't just pick a few random numbers and add those to the words. That doesn't make sense the way it does with an image. So we have to do something else so that we can still apply consistency regularization to NLP. And I'm going to cover 3 ideas, 3 ways of doing it. So one is from Mioto et al. And their idea is, well, words are discrete, but words embeddings are continuous. Those are just vectors. Let's just add the noise to those instead. And then this other result is my own research I've been doing in collaboration with Google Brain. And there are 2 ideas here. There's a simple one, which is called word dropout. You can almost guess what that is based on the name, but I'll present it a bit later. And then a more sophisticated approach called cross-view consistency. Okay, so we're going to start with this Mioto et al. Paper, and it's called Virtual Adversarial Training. So first, as I mentioned before, they apply noise to the word embeddings rather than the words themselves. And there's a really important detail here, which is that in order to make this work, you have to put some kind of constraint on the word embeddings. If you didn't do this, the model could just make the word embeddings really, really large, and then whatever kind of noise you add to them basically wouldn't matter compared to the original size of the word embeddings. So what the authors of this paper did is constrain the word embeddings such that in each dimension they would have a mean of 0 and a variance of 1. And this way you can still do this consistency regularization effectively. The second point, which is also pretty interesting, is how do you pick which noise gets added to the inputs? And so far I've just been presenting it as you pick the noise randomly. But this paper does something different. It picks that noise adversarially. So what does it mean to adversarially pick the perturbation that's added to the input? Well, this connects to an idea that I imagine a lot of you have seen before because it's gained a lot of press and attention. It's actually a really interesting property of neural nets, and you see it especially in computer vision. So here we have an image of a panda, and we can train an image classifier that does a great job and says, this is a panda with 99% confidence. But it turns out that you can actually tweak this input a little bit by adding what looks to a human like completely random noise to it. And you can see that the outputs after adding those noise look to a person is completely indistinguishable, right? Those two pictures on the right still totally look like pandas, but this actually completely fools the model into thinking the top one is a shark and the bottom one is a goldfish. So I think this is interesting on its own because it kind of shows that neural nets aren't nearly as smart as we might think they are. They, on the one hand, get basically human performance on image recognition. On the other hand, they exhibit this really weird lack of robustness to these adversarial noise. And an interesting thing to think about when you're thinking about adversarial examples is that this could actually have pretty significant effects for security. So there was one kind of fun recent paper which showed you could basically construct a patch, so a little really bizarrely colored circle there. You could put it next to an image in real life, take a photo of it, and still confuse the model. So here, I'm not sure what that says. The model, oh yeah, the model thinks that banana is now a toaster because there's that weird circle next to it. So this is kind of absurd because a person is nowhere fooled like this. And in this example, you can't really say any harm is being done. I don't think there's any case where you'd really care too much if your computer thinks a banana is a toaster. The effects aren't that catastrophic. But you could also do this kind of things with a stop sign. So that's what this picture shows here. Is another paper basically came up with these adversarial tweaks, these little black and white stickers you can add to a stop sign, and actually cause a computer vision system to no longer recognize that this stop sign is a stop sign. So maybe it'll think it's like a yield sign instead. So if you have a self-driving car and it's using computer vision to figure out what the signs are, this is obviously a pretty big problem. So I guess for the time being, this isn't necessarily a concern. I guess you could say, well, why not just take away the stop sign instead of adding some stickers to it? But it's actually growing as an area of research, is this idea of AI security, right? If AI is becoming more prevalent and more common in our lives, and they have pretty weird security vulnerabilities like these adversarial examples, people are starting to work now on building up systems that are robust to these adversarial attacks and aren't as fooled as easily. So that's kind of an active area of research that's pretty interesting. Okay, the one thing I haven't said is how exactly do you come up with an adversarial example? And the answer is you basically turn neural net's own tool against it, which is gradient descent. You look at the gradient of the loss function not as normal, which is with respect to the weights of the network. You do it with respect to the input of the model. And the gradient tells you exactly, right, how you could change the input such that the loss function increases. So normally, when you're training a model, you subtract the gradient times some small learning rate from the weights. Here, instead, we're going to add the gradient times some epsilon to the input. And you could repeat this multiple times. And basically, because we know the full kind of dynamics of the neural net and we can do gradient ascent on it, we can construct precisely the noise that most confuses the model. And that's how you make these adversarial examples. And then let's just bring it back to supervised learning, right? How semi-supervised learning, how does this connect? Essentially, it means that when we're selecting our noise vector to be added to the word embeddings, we're going to compute it as the gradient of the loss with respect to the input, with respect to the word embeddings, and then make it a unit vector and multiply it by epsilon. So we have this fixed size tweak to the input. And you can think maybe the reason this is so useful of an idea is that we have this ball around our unlabeled example, and we want the model to be consistent there. But in a high-dimensional space, just randomly sampling points in that ball is probably not going to cut it for really ensuring this consistency constraint we would like to have on our model. So adversarial training lets you pick that tweak to the input much more carefully. And that can improve results quite a lot, as we'll see. But first, let me just ask, is there any questions about this or about adversarial examples in general? OK, yeah, question.
So I guess for this, you also have to train, optimize it twice, right? Compute gradients twice.
Yeah. So the question here is, don't you have to compute gradients twice to do this? And the answer is yes. So this is actually almost twice as slow as regular training, because you have to compute the gradients once to compute what that noise vector is. And you have to compute the gradient a second time to actually update the model parameters. So that's like pretty big downside to this approach. All right. So let's move on to results for this method. The baseline here is actually going to be what I presented at the beginning of this talk, which is the autoencoder pre-training. So that's what that first row of this table is. It's on a sentiment classification task, by the way. So we start with already a really strong baseline, which gets good results. But adding this consistency regularization with random noise decreases results further. And then if we use this adversarial training idea, results get even better. So this seems like a pretty nice technique. What I've been working on a bit is, can we use this same consistency idea, but do it in a much simpler way? So here's a way simpler way of corrupting the input rather than adding adversarial noise to the embeddings. What we're going to do instead is just, with some probability, drop out words, which means replacing them with some special token. Let's call it removed. You can think of it a bit like an UNC token. And then still encourage the model to give the same prediction regardless of whether these words are dropped out or not. So this is a lot simpler than adversarial training. And actually, interestingly, it works better in a lot of cases. I think why is probably because since words are discrete, it's more natural to do this sort of discrete transformation when you drop out words rather than adding noise to the word embeddings. And one thing to think about is an effect of adding noise to word embeddings is really what's going to happen is it's going to push all the word embeddings away from each other such that adding noise to one won't cause it to be confused for another. So that seems kind of useful, but maybe not totally ideal. OK, a couple questions. How about in the back?
So when you add noise to the embeddings, at least for the vision case, how do you decide the magnitude of what that noise is? Like in the vision case, it's easy because you can see the image and kind of tell. Is there some analysis done for word embeddings? Because that also might be a reason that maybe they're really far out or something like that in embedding.
So yeah, so the question is, so say in this equation, how do you decide what epsilon is? How do you know what magnitude it should be? And for images, you can look at the image and figure out what epsilon is not totally making the image undecipherable, but you can't as easily for NLP. I guess the answer is that epsilon is a hyperparameter, and you can tune it like any other hyperparameter and just figure out what works best on your data. What you can do at least is figure out how far apart are two very similar words in the data set. and then say, OK, epsilon should be around that size. Other questions? Yep.
Would it be better, did you try, instead of adding the word remove, just adding a random word?
So that's also a good question. I haven't actually tried that. I guess my concern there is that if you drop out a word, it's not really, it's removing meaning, but it's not changing meaning. Where if you change words, it may start exposing the model to these weird sentences that would never exist in real life, and that might mess things up. So I'm not convinced if that would actually work better, but I think, yeah, that'd be an interesting thing to try, and I haven't tried it.
What humans do often, like I might mistakenly hear one word for another word, and it's part of having a good model is to recognize when that's happened. And so by giving it a random word, it's going to have to learn a better language model implicitly.
Yeah, OK, that's a really good point. So the point is that replacing a word with a random word might force the model to have a really good sort of understanding of language so it can recognize when that's happened and when something weird has gone on with a sentence. Yeah, that seems like a good point. Maybe I'll try it. OK. So that already works pretty well. It's pretty nice. Let's just focus on the top for a second. Here is just what word dropout looks like, right? We have some input sentence, and we're training our model to still be able to handle that sentence well in this different view where some of the words are missing. What we were looking at is, OK, wouldn't it be better to expose the model to a whole bunch of different views of the input at once, right? So let's say we're doing a word level task like NER. Let's say we're making a prediction about the word Washington in the sentence they travel to Washington. You could imagine training the model to be consistent in its predictions when all of the words to the right of Washington are removed, or all of the words to the right of Washington are removed as well as Washington itself, and so on. So it seems great and really data efficient to have many views for an example instead of a single randomly created view of the example when you're enforcing this consistency in predictions. It also seems like there's a big trade-off here, though, because in this bottom case, well, now there's 4 views, and you're actually using a different view for every word. So are we making our training algorithm 4n times as slow, where n is the length of the sentence? And basically, we have a trick for getting around this. And this trick is that instead of giving the model a bunch of different inputs, all with slightly different words crossed off, we're going to add extra prediction layers or extra softmaxes to the model, and we're going to construct them in ways such that the model naturally won't be able to see everything. So I'll get a lot more specific about that later, but just to provide one example of what that would look like, if you have a bi-LSTM in your model and you only make a prediction from the forward LSTM, so not using both LSTM's inputs, then that's basically equivalent to saying the model can't see any words to the right of the current one, because that's how LSTMs work. They only see previous context, not future context. So I think it might be more clear later when I show a specific example, but that's the rough idea. And then what our loss function is going to look like is we'll have a bunch of these extra softmaxes, all of which see some restricted view of the input. And we're going to say all of these have to be consistent with our main softmax that sees everything. So here is what the training procedure looks like. Labeled example is exactly standard supervised learning. So if we're doing NER, our model can learn that Washington is usually a location. And then on the bottom, on an unlabeled example, our model will first make a prediction. And hopefully, because it was in the training set, it'll guess, OK, Washington is likely a location. And then it's saying that all of these other softmaxes that see less of the input have to match that prediction. So in particular, if you look at the first softmax there, what it sees is they traveled to, and it has to guess that the next word is a location. So from this, we can hope that our model is going to learn something new. It's now going to learn that they traveled to is a phrase that's usually followed by a location. So this is how the sort of bootstrapping works. So the model improves from its own predictions. Any questions on that? Okay, good. Let me talk a little bit more specifically about what are all these extra softmaxes doing. And so here's a figure. It's showing a standard BILSTM model. The red arrows are just standard softmaxes where both BILSTMs are taken as input. The blue arrows are these auxiliary softmaxes that see less of the input. So for example, there's one that's attached to the forward LSTM and is predicting the current time step. So you could say that model is not seeing anything to the left of the current word. You could also do something where, like, taking the forward LSTM states, and instead of trying to predict the current token, you try to predict the next token's label. So this is, you could actually almost think of this like a language model, right? But a language model predicts what word comes next in the sequence. This model is predicting what class comes next in the sequence. So rather than is the next word Washington, it's predicting is the next word a location versus something else. You could also apply this same idea to machine translation. So here is a standard attentional seek-to-seek machine translation model. And normally what you ask the model to do is, given the previous predictions and the input, you predict which word comes next in the sequence. But you could also add a few additional softmaxes. So you could add one that does this. It's not predicting the next word in the sequence. It's actually predicting what word comes, the word after next in the sequence. So what's the future word? And the other auxiliary prediction layer we add does dropout over the attention. So here, the attention to the third word is crossed out. And this is another way of, similarly, we want to restrict the view of the models of the input. And now we're not allowing it to attend over certain words. So it has to compensate somehow and be able to still make a good prediction. Okay, so those are the prediction layers. Just want to briefly kind of pitch why this is a good idea compared to just word dropout. And the answer is that it's much more efficient. So right, in terms of data efficiency, word dropout is only exposing the model to one view at a time, which is the sentence with a couple words crossed out. In our case, now we're exposing the model to many different views at a time. Basically, in the case of sequence tagging, for 4n different views, right? So that seems great. And the computational cost is nowhere near 4n times as much. It's much more efficient because we're only adding softmaxes. And when training a big neural network, the LSTM is by far the slowest part. So adding these extra softmaxes doesn't really hurt the runtime. So you're getting all these extra views for free, kind of. Okay, let's get into the results of this method. Oh, question?
You like intersperse these things kind of randomly throughout training, or does it see all the views of a given thing at the same time?
The question is, are the views kind of mixed up in training, or do you see all the views at once? The answer is all the views at once. So all of these prediction layers will be running simultaneously on every unlabeled example. And then supervised learning, as with all of these consistency regularization methods, is done as normal. So yeah, actually that's a point to mention here is all these extra softmaxes are only used on the unlabeled examples during training. And at test time, you actually throw them out and don't even look at them. So their only purpose is to improve this like representation learning in the model. Okay, so here are previous work. And we evaluate our model on a bunch of tasks. One thing to point out is that some of these numbers here are semi-supervised, so the chunking and NER numbers are from Elmo, but the rest are purely supervised. And I guess partly that's because semi-supervised learning is in its early days, so it's actually not that common practice yet. Here are our supervised baselines. So you can see they're, in some cases, significantly worse than prior work, except for machine translation. Here are basically two comparison points. So the first row of this table is virtual adversarial training, which I showed earlier. It does improve over supervised learning a bit, but actually it's kind of interesting. This much simpler word dropout approach works better in most cases. Actually, for virtual adversarial training, we just couldn't get it working for machine translation. So that's why one of the entries in that table is blanked out. Okay, and then this is the results of the cross-view consistency method instead. Accuracies are a lot better on all the tasks, and one thing I was pretty happy about is that it actually outperforms Elmo, even though it doesn't have nearly as large of a model and doesn't require this massive pre-training phase. And then, oh, we have a question.
When you compare those results from CDC with, say, supervised, are you training on the same data set, or do you just take some labels and you train them out and you do that?
Oh, yeah. So that's a good question. I wasn't clear about the setup here, which is what is the labeled and unlabeled examples. Here, the labeled examples are the same for all of these, which are just standard data sets in NLP. The unlabeled example comes from a totally separate corpus. So it's called the billion-word corpus, and it's a bunch of news articles.
In the supervised row, they have no access to that.
And in the supervised row, yeah, so the supervised row does not have access to unlabeled data, whereas the other three rows below that do. Okay, here is just the last piece of results, and I think they're kind of interesting. So there's a different graph for each task here, and you can see that on the left, the plot is showing what happens when you actually reduce the amount of training data to the model. So I think one result that's pretty unsurprising is the less training data the model has, the more it benefits from semi-supervised learning. So there's some indication these approaches are particularly useful for kind of what I was mentioning at the beginning of the talk. If you think of low resource languages or tasks that aren't as well studied and don't have as much data for, this might be particularly useful. Another thing that I found pretty surprising about the model is that actually using only 25% of the labeled data, the model is already, the semi-supervised model is as ready good as a fully supervised model. So yeah, much better data efficiency if you apply semi-supervised learning. The other four plots on the left-hand side, or your right-hand side, sorry, show what happens when you increase the number of LSTM, the number of units in each by LSTM. And typically, if you're training a supervised model on a small amount of data, your model starts overfitting pretty quickly once it gets too big. So you can see that most of the green lines, which is the supervised model, accuracy starts going down for some of the tasks as the model gets bigger. And it seems like with semi-supervised models, that effect is a lot less. So I guess it's a little hard to see, but I think there's some reason to be hopeful that semi-supervised learning might make it possible to scale up models a lot more, even when the data set is small. And previously, that's been kind of an obstacle in getting neural nets to work on small data sets. Okay, so that is it for this lecture. I guess I'm about 5 minutes early. I can take questions at the end as well. Just to kind of summarize at a really high level what we talked about, there's been a lot of recent work on semi-supervised learning, and especially if you look at things like Elmo, the results are really amazing, and you might expect this to be much more commonplace in the future, in the next few years. And one thing particularly nice about it is it allows you to get those benefits of large scale that deep learning systems really can take advantage of, even when your data set is small. And okay, any last questions, I guess? And otherwise, we can just end the lecture. All right, thank you. Good luck with all your projects. it.